So I'm going to be talking about joint moments of the multi-species Q boson. So I'm actually going to start with a simple model that's related to the Q boson. This is called the asymmetric simple exclusion process, often abbreviated ASEP. And we're going to consider a one-dimensional lattice here. And at each lattice site, there can either be a particle represented by these black dots or a hole represented by these white dots. So this process is going to evolve randomly. And so each particle has an exponential clock of rate 1. And then when the clock rings, it chooses to jump either left or right, probability alpha or beta. And the exclusion occurs if a particle tries to jump to a site that's already occupied. So in that case, the jump is blocked. So no jumps can occur here. And you can define a height function that just goes down every time there's a hole and up every time there's a particle. So one of the things I did during the pandemic was teach myself a little bit of Python. So I know just enough Python to make this animation. So we're going to consider step initial conditions. So the mth leftmost particle is at m. So initially, all the particles are densely packed to the right of the origin. And the height function is this V shape. And as it evolves, you can see it's this random kind of jagged curve. So it fluctuates around a parabola. And we're interested in knowing what the fluctuations are. Okay, so I'll talk about that on the next slide. Actually, 2 slides. So yeah, so these are the fluctuations. So the relevant statistic here is the 100th rightmost particle at time 2000. So I just used the Texas A&M supercomputer for an hour, and that gives just over 2,000 samples. And so this is the distribution you get. So this is similar to Massachusetts in that it's blue and left of center. So, in contrast to the Gaussian, it's not centered at 0. It's, the mean is negative. Okay, so this distribution has been studied before. So I'll give a little bit of historical context. So these are the single point fluctuations with step initial conditions. So there's other works, for example, with stationary ASEP. But just for the sake of time, I'm focusing on step initial conditions. So back in 81, Roast considered TASEP. So that's when it's totally asymmetric. So jumps only go to the left. And he proves a law of large numbers. So you scale the particle, the tagged particle, linearly in t in time, and the position of that is linear in t, and it converges almost surely to to some number. And then a few years later, Thomas Liggett extended this result for ASEP. So it's, alpha doesn't need to be 1. And then we have a central limit theorem for TASEP. So you look at the position of the particle and you see how much it fluctuates around its average. And you have this 1/3 scaling exponent, which is common for models in the KPZ class. And it converges to something called the Tracy-Whittem distribution. And this was unsurprisingly first discovered by Craig Tracy and Harold Whittem in the context of random matrix theory. So this also occurs as the fluctuations of the largest eigenvalue of a GOE random matrix. And then a few years after that, Tracy and Whittem showed the central limit theorem for ASEP. So no longer totally asymmetric, partially asymmetric. The reason I'm talking about ASEP is that this is a universal distribution in the Kardar Parisi Zhang universality class. So this is analogous to the Gaussian distribution, right? So the bell curve occurs in a lot of contexts. And the Gaussian distribution is named after Gauss, but it was actually first discovered by Adrian a year before. And the reason it's not named after him is because he was working in the United States at the time. And back then the US was a new country and wasn't known for mathematical research. And his result was actually the first mathematical discovery in the United States. So I made this slide on Independence Day, so I was feeling patriotic that day.
Sorry, can I stop you just a second?
Yes, go ahead.
And so what is the subscript M? You have X of MT.
Oh, yes. It's the position of the nth leftmost particle. So as t goes up, you look at a particle that starts farther out in this direction.
I thought each side can only have one particle. So I'm just trying to understand this drawing.
Oh yeah, so so x1, if for example, is the leftmost particle. So maybe I'll go back. So like for example, this is x1 and this is x2 and this is x3. So it's a tagged particle. So you just follow the position of this particle.
I see.
Yeah.
And so the distribution is the position of the nth particle.
Yes, that's right.
I see. Okay.
Mm-hmm.
And so just one last question, if we're on this slide. So you have these two particles which are together, right?
Yeah, you can view this either as a particle or white particle or a lack of particle.
No, never mind. The two black ones, right?
Oh yeah, these two black ones, yeah.
So there's no probability for them both to move in one of the directions?
Oh yes. So in a continuous time process, the probability of two particles moving at the same time is infinitesimal. So there's zero probability that both jump at the same time. Yeah, that's a good question. Yeah, so there's no probability of two jumps occurring at the same time.
Maybe the question just revealed that I don't understand. So that's why it sounded good. So I mean, so you have like a lattice, right? You have a one-dimensional lattice, and each you have some initial condition where you sprinkle these black ones.
Yeah, the initial conditions are where all the particles start here. So those are the initial conditions I'm considering.
Okay, I think I'm starting to understand. So it's like a kink, and then you start letting them jump around.
Yeah.
Okay, thank you.
Yeah, that's a good question. Yeah, it matters that's continuous time. Okay, so next natural question is multipoint fluctuations. So if you look at the positions of two tagged particles, so each one is going to fluctuate as a Tracy Whittam, and they're correlated somehow. So for ASEP, the fluctuations are the Airy-2 process. So Johansen proved this using some determinantal formulas for ASEP. And the Airy-2 process was discovered a year earlier by Preyhofer and Schwann in the PNG model. And there the spatial fluctuations have a 2/3 exponent. So if the distance, the distance between the particles scales as t to the 2/3, that's the non-trivial distance to look at. And generalizing to ASEP, where you don't have determinantal formulas, is a lot harder. So it took almost 20 years. And it was only last year that Germany Castell and Surav Sukar proved multipoint fluctuations for ASEP. And they actually did this for general initial conditions. And the only other result for multipoint fluctuations that I know of for a non-determinantal process is by Evgeny Dimitrov. He looked at the stochastic 6 vertex model and proved 2-point fluctuations. Okay, so the title of my talk has multi-species in it, so I should talk about multi-species models. So I'll introduce the two-species ASEP because it's a little bit easier to describe the two-species ASEP than the Q boson. So this was introduced by Thomas Liggett in 1976. So here you have two species or colors of particles. So these are often called first class or second class. So the black particles are the first class particles and the red particles are the second class particles. So each species of particles evolves as an ASEP. And the interesting interaction is when you have two particles of different classes next to each other. So if a first class particle tries to jump to a site, it's occupied by a second class particle, then it makes a jump and it forces the second class particle to switch places. And the second class particle can't jump to a site occupied by first class particle. So if this red particle tries to jump there, then the jump is blocked. So this system evolves similarly to the way the real world works. So the first class particles do whatever they feel like and just ignore the second class particles. And the second class particles can't do anything about it. So this can be viewed as two coupled ASEPs. So if you're the type of person who says, I don't acknowledge the existence of a class system, or I don't see color, so this is sometimes called the colorblind projection, then this line here evolves as an ASEP. Or if you're the type of person who says, I only care about the first class particles, the lower class particles are invisible to me, then this also evolves as an ASEP. So for fluctuations of the multi-species models, there's a lot less known or even conjectured. So
wait,
this
you can only have one particle per site, right?
Yeah, that's right.
So what do you call them bosons then?
Oh, yeah. So each site can only have one particle, but it can either be a first class particle or it can be a second class particle. So if you look at this top line, you see that there's only one particle per site.
It sounds more like a fermion to me. But,
yeah. So this is a fermion. So I'll talk about bosons in a few slides.
Okay.
Yeah, this is determinantal point processes were originally called fermionic. Yeah. So yeah, this is a fermion exactly. Right. So so this slide is intentionally sparse. So the only proven result for multi-species models came out pretty recently. They considered another model called the AHR model, and they showed the crossing probability as an F2 times the Gaussian. And it's actually not even clear what the right question is. That's because, but for example, I'm going to give a different statistic here. So my result's not going to be F2 times the Gaussian. Okay, so now I'm going to introduce the Q boson. So it's equivalent to the Q TASEP, which was introduced by Borodin and Corwin. So if you consider a TASEP where the jumps go to the right, but now the jump rates are dependent on the gap in front of them. So it's 1 minus Q to the gap. So here the gap is 2, so the jump is 1 minus Q squared. Here the gap is 1, so it's 1 minus Q to the 1. Here the gap is 0, so it's 1 minus Q to the 0, which is 0. And we're going to have a rightmost particle. So here the gap is infinite. So the jump is just 1 minus 0, which is 1. Yeah, so the gaps evolve as a Q boson. So for example, here the gap is 1. So there's one particle here. Here the gap is 2, so there's 2 particles here. Here there's no gap. So there's no particles here. And here there's infinitely many. So you can have infinitely many particles occupy a site. So in probability, this is sometimes called a zero range process. So have an animation here too. So we consider an initial conditions where you have, so step initial conditions, you have infinitely many particles here, and particles just jump in from the origin. And then as particles jump in, you can see that this thing is going to grow. So this line is just the number of particles at each site. So it once again, it's this random curve. and it fluctuates around some deterministic curve. And we're interested in knowing what these fluctuations are. Okay, so I guess I restarted. Yeah, so initially there's no particles here, infinitely many there. So again, I just ran the Texas A&M supercomputer for an hour. Again, we're looking at, so for QTASEP, we're looking at the 200th rightmost particle at time 2000. And again, the fluctuations are the Tracy-Whittem distribution. So this was proven by Ferrari and Vito in 2013, and they have some technical conditions. And a year later, Guillaume Barracon removed the technical conditions. And I think he actually considers a slightly more general model where you have two speeds of particles. Okay, so then, so the multi-species Q boson, which is the thing I'm talking about in the title, was introduced by Takayama. So the germ points are pretty simple to describe. So here it's 1 minus q squared because there are two second-class particles, but it's slowed down a little bit by q squared, and the 2 is because there are two first-class particles here.
So, sorry, can I ask a small question about the previous slide?
Yeah, go ahead.
So I understand what's going on. So what is the distribution? What does it mean that there is -1 when you have x of 200 of 2000?
Oh yeah, that's a good question. Yes, so so you look at x of 200 divided by 2000, and then you subtract the law of large numbers, so c1 minus t, and then you divide by another constant times, you divide by t to the 1/3. So this is what you get after you do the rescaling.
No,
yeah, that's a good question.
But so there is some mean, and you want to see the fluctuations around it?
Mm-hmm. That's right, yeah.
So the question is whether the 2000 site is occupied or not? Whether there is some?
No, so time is 2000, and you're looking at, you're looking at the position of the 200th rightmost particle in QTASEP.
I see. Okay. Okay. Thank you.
Mm-hmm. So again, the multi-species Q boson can be viewed as coupled Q bosons. So the first class particles sort of ignore the presence of the second class particles. And if you take the colorblind projection where you don't see any color or class, then this also evolves as a Q boson. Okay, so this is my main result. So there's a lot of symbols on here, but I can try to explain it in words. So we consider a generalization of step initial conditions where you have infinitely many first-class particles at one site and then infinitely many second-class particles somewhere to the right of that, and infinitely many third-class particles somewhere to the right of that. The particles jump to the right. So that's the natural initial conditions for the multi-species models. And it's not quite as clear what the analog would be for ASEP. Yeah, so here it helps you have infinitely many particles occupying the site. Now we're going to define this n to be nxj to be the number of particles of species up to j to the right of x. And then we're going to look at the nth q moments of n at a single point. So because of shift invariance, you can just take the point to be 0. So looking at this expectation, at the right-hand side here, we have a single species model, but we're looking at the multi-point fluctuations, or multi-point moments. So just in words, the single point fluctuations of the multi-species Q boson are the same as the multi-point fluctuations of the single species Q boson, which should be the area 2 process. So then a natural conjecture, which as far as I know hasn't been stated in the literature before, although maybe someone knew it, just didn't write it down, is that the single point fluctuations of the multi-species Q boson and other models in KPZ with step initial conditions are the ARI2 process. So similar statements were proved in more generality by these authors for stochastic vertex models in the quadrant. So the result I'm presenting here doesn't immediately follow, as far as I know, from these results. And that's partially due to the degeneration from stochastic vertex models and continuous time processes. Can be done in more than one way. And also the boundary conditions, I guess, are different. Yeah, so I don't think it follows from those results, but if someone out there listens to this talk and tells me I'm wrong, I'm open to being corrected. Okay, so the rest of my talk is devoted to just proving this. So this is, yeah, so I have 3 sections, I guess, spanning five papers. So the first step is to use Markov duality. So that reduces calculations of the nth Q moments to the n particle system. So initially you have an infinite, you have a particle with infinitely many systems, but you can reduce the calculations to a finite particle system. And second, once you have that reduction, you need to analyze the finite particle system. So you write the transition probabilities of that system. And then once you have the transition probabilities, you need to do something with it. And this is going to be a symmetrization identity. So each of these steps will be a section that I wrote up here. Okay, so I'll start with Markov duality.
Can I ask you about the initial conditions that you mentioned before? You said that they were natural. And
oh yeah, I guess it was natural for me. Just I don't have a better definition of natural other than just it felt natural.
Oh, I'm just saying whether this is motivated by some kind of problem that that gives you a naturality.
Oh yeah. So I guess
whatever.
Right. So you have this colorblind projection where you project down to where you just pretend you don't see any color. And then when you do that projection, it should still be step initial conditions. So in that case, you need to have infinitely many first class particles somewhere. And then if you put all the second class particles, so if you put all the second class particles the same size as the first class particles, then you have Q'd infinity, so the second class particles never jump. So that's not so good. So the next natural thing to try is to just put the second class particles somewhere to the right, or I guess to the left of the first class particles. And then if you take that projection, that's still Q boson with step initial conditions. Yeah, so I guess if you hold the idea that the colorblind projections should still be step initial conditions, then this is more or less the only initial conditions you could really look at.
Where do the step initial conditions come from?
Yeah, so if so if you consider Q ASEP, so all the particles are to the left of the origin, then that corresponds to all the gaps being 0, except for one gap being infinite. So step initial conditions in ASEP correspond to just infinitely many particles here. I guess originally, for TASEP and ASEP, step initial conditions were considered just because, it's easier to say things for step initial conditions than generic initial conditions. Yeah, so I should also say, I'm only talking about step initial conditions where you get F2, but if you consider different initial conditions, you'll get a different fluctuations.
Yeah, sure. I'm just wondering why. I mean, it's you can have an infinite set of problems that you can define.
Yeah, exactly.
So I'm just, but you're choosing to think about a very particular one. So I'm just wondering whether you have some motivation.
Yeah, yeah, that's a good question. So it's just, if I could go back, this result about F2. Yeah, so if you, so in random matrices, you have different sets of random matrix ensembles, and somehow the most natural ones are F2 and F1. And so, once this result was known, that F2 occurs a lot, it's sort of natural to just try the first step as first step to be step initial conditions, just because that's where you expect the F2 distribution to come up. And then for generic initial conditions, it's not really clear that the limiting distribution is as nice as this one. I can plot that Tracy-Witten distribution, but if you take arbitrary initial conditions, it's not really clear what this distribution would be.
Yeah, I think, sure.
Yeah. Yeah, that's a good question.
While we're asking, could I ask another question?
Yeah, sure, go ahead.
So when we're doing this like central limit theorem, for example, I do understand right that the particle you're considering is kind of moving to the right in the list.
That's right.
Okay. Do you have like sort of an intuitive reason of why I would want to do that, or is it just sort of what you have to do to get a good limit?
Yeah, it's sort of so it's sort of analogous to the central limit theorem in probability. So so if you just take a single particle on a lattice, so no other particles, right? It's just one particle moving, and you look at how that one particle jumps, right? Then that's going to move. That position is going to be linear in time, and then it's going to be t to the 1/2 with a Gaussian. So if you have a bunch of particles, you sort of want to ask an analogous question.
Wait, sorry. I think I phrased badly. So somebody asked before about like, why are you considering the index MT?
Yeah.
And so as you said, if you have a single particle that's just moving independently, then you get the nice limit that you described.
Yeah.
So I would expect to be doing something like that, where I'm following a single particle. But instead, I'm following sort of, at time 1, I'm following a certain particle, and at time 2, I'm following another particle. Time 3, I'm following a third particle. And
it's just so if you scale this in T, that's just what you need to do to get something non-trivial. Because if you just looked at like the rightmost particle, then it doesn't feel the presence of the particles to the left of it for T7.
Right.
So you sort of need to take this to infinity.
Oh. Okay, so it's not necessarily important that I'm doing m times t, but rather the important thing is that I'm looking at, how do I say this? Is the idea that at the limit, I should be looking at a particle which is like infinitely deep into the stack of particles?
Yeah, that's right.
Okay.
Yeah.
Okay. And if
that's a good question. It's the first time you look at the model, it's not really clear that that's the right statistic to look at.
So if I took like m times t squared, for example, would I expect to get the same limit?
So if you took if you took m times t squared, then you're too far into like here, and then you would just get 0.
Oh, that's weird. Okay, thank you.
Yeah, these are good questions. Okay, so Markov duality is a general property of Markov processes. So you let eta and zeta be Markov processes with state spaces x and y. And d is some bounded measurable function. So you look at the expectation of d of eta and zeta, And on this side, you let eta evolve in time, and you fix eta. Here you let zeta evolve in time to fix eta. And duality just says that these two are equal for all times. And an equivalent definition that I'll use for discrete state spaces is that if you have a generators and you view them as x by x and y by y matrices, then D is viewed as an x by y matrix. Then you have this intertwining. Yeah, so I should say the generator of the Markov process is basically the derivative of the transition probabilities. So the generator defines the jump rates. So it's just a matrix where you have the jump rates written down. Okay, so duality is this intertwining. So for some historical context, you can consider exclusion processes on an arbitrary graph G. So this G here has 254 vertices. And it might be a little hard to see, but I have some particles represented by blue dots. So there's some blue along the bottom here. And there are three or four clusters of blue arranged in this triangle. And you have a symmetric stochastic matrix P with rows and indexed by your graph. So this performs exclusion. So if a particle at X tries to jump, it chooses a site Y according to these probabilities. And it jumps there if it's unoccupied. Otherwise, the jump is blocked. And so duality holds for symmetric exclusion processes on a graph. So you have two ways of denoting a particle. There's particle variables. You denote the number of eta of X is the number of particles, so 0 or 1 at the site X at time t. And you can also define the occupation variables, which is just a set of occupied variables. So you look at the probability that every particle in A is occupied in eta, and here you let eta evolve. Here you let A evolve. Duality says these two are equal. So one reason this is useful is that eta of t can have infinitely many particles, whereas A as t can have finitely many particles. So you have some calculation infinite particle system, but you can do it in a finite particle system. So once you have this, the actual question is to ask, what's the duality for the asymmetric processes? So when I was talking to Tom Liggett a few years ago, I guess before he passed away, he told me that in the 80s, he and some collaborators trying to find duality for the asymmetric models. But they weren't able to do so. And part of it is just because the algebraic machinery hadn't been invented yet. Before I get into that, first I'll say what the result is. So you like QB squared root of beta over alpha. So this is the asymmetry parameter. And this function is non-zero only when there's a particle in eta for every particle in A. And for each particle in A, you count the number of particles to the right of eta. You take Q to 2 to that number. And you have to add 2x. And it's worth mentioning if you take Q equals 1, it just gets the simple case of Spitzer's result back. So this generalizes Spitzer's result on a one-dimensional lattice. Okay, so now I'm going to talk a little bit about the algebraic machinery here. So we're going to associate to each particle configuration a vector. So all particle configurations will be a vector space, and that'll be a representation of some algebra. So we're going to look at just C2. So this has a basis 1, 0, and 0, 1. So 1, 0, you associate a particle, 0, 1's a whole. And yeah, so on L lattice sites, you just take a tensor product of C2. So I wrote out the 4 possibilities when you have 2 lattice sites. And then the algebra acting on this representation is SL2. So these are traceless 2 by 2 matrices. They have a basis traditionally denoted E, F, and H. And E and F are creation and annihilation operators, because if you just multiply E onto a hole, you get a particle. So it creates a particle, and then F does the reverse. So it takes a particle, turns it into a hole. So that's how the representation acts, that's how the algebra acts in a single lattice site. And then for multiple lattice sites, you have something called the coproduct. So the way this works is it acts on each lattice site and just fixes all other lattice sites. And then you take the sum over all lattice sites. And you'll notice this is symmetric in the left or right directions. So if you just switch left and right, you get the same thing. If you're familiar with Hopf algebras, this is co-commutative. If you're not familiar, that's okay. You don't need to know what that word means. So the relationship to symmetric exclusion process is that the generator can be written as the coproduct of this special element called the Casimir. And one thing which makes it special is that it commutes with all other algebra elements. So Cx equals xc. So you take C to be, you take L to be the coproduct of C, and then you take X to be some appropriate annihilation operator, or series of annihilation operators F, and D is the coproduct of F. So Cx equals xc becomes LD equals DL. And since L is symmetric, this is L equals L transpose. So this is the equation defining intertwining. Yeah, so the annihilation operator, you just take your infinite particle system, you annihilate until you find out many particles. Right, so then the asymmetry occurs through quantization. So in between Spitzer's duality and Schutz's duality, the 24-year gap, quantum groups were discovered. The main idea is you just Q deform everything. So the biggest change is the coproduct. So this is now different in left and right. So you switch left and right, you get a different coproduct. And when Q goes to 1, you recover the original coproduct. And again, you can do something similar here. So you can write the generator as the coproduct of a central element, which could be all the algebra elements. And so this is no longer symmetric, but ASEP has this probability called reversibility. And this is a detailed balance condition. It basically just says that the generator is related to its transpose with this conjugation. So you just plug that in there and this gives you duality. So this was work at least 25 years old. More recent work, I guess, 7 years ago. Natural step is well, they give this framework where you instead of considering SL2, you consider an m+1 dimensional representation. So now you can have m particles occupying a site. So I guess this is neither fermionic nor bosonic, I suppose. And the asymmetry parameter is Q to the m. And so in particular, this paper gives you framework for producing duality functions. And when m equals 1, generally this shoots this duality. So they call it ASEP QJ. So J is m over 2, because I think in physics notation, it's more natural to take half of the dimension. It's called the spin, higher spin representations. At least for me, a natural thing, if you see that, is to say, oh, let's replace SL2 by SLN. So if you do that, you get an n species ASEP I talked about before. So this is a product of Schutz duality functions, one for each species. And its indicator is for each ith species particle in the dual process, the particle at that site in the process eta has to be between 1 and I. Yeah, so this result came out about a month before Blitzky and Schutz proved, I guess, the same result and did some applications. And then the same thing happened a year before for n equals 2. So I guess it was time for people to work on this problem back in 2015. So if you take ASEP qj, so the asymmetry parameter is q to the 2j, and you take j going to infinity, you get a totally asymmetric model, and you actually get the Q boson. And so you, if you just took that duality function and you take q going to 0, you get, sorry, if you take j going to infinity, you just get 0. So what you need to do is apply a charge parity symmetry. So you reverse the ordering of the particles, the direction of the jumps. So now eta has particles jumping to the right and A has particles jumping to the left. And you just get a product of, yeah, so these are actually just the Q moments, the relevant statistic that I mentioned before. So this duality function is just the Q moments of the multi-species Q boson. And it's a multi-species version of a duality that occurred before. Okay, so that was so that's one way to prove this. So I guess I like this result enough that I wanted to see how else it generalizes. So the next thing I'm going to talk about is duality in vertex models. So both ASEP and Q boson are degenerations of stochastic vertex models. So here are the 6 weights of the stochastic 6 vertex model. So the number of arrows coming from the southwest directions equals the number of arrows going out from the northeast directions. So these are the 6 weights. And in the stochastic case, these are normalized to be 1. So here, both of these are 1. These two sum to 1, and then these two sum to 1. So these weights, yeah, you can view this as a Markov update. So this is your input, and then you have a random output. So this arrow comes in, so it either goes up or to the right with these two probabilities to add up to 1. So this can be viewed as a discrete time particle system. Right, so here you have arrow, nothing, arrow, and then nothing comes in. So this arrow decides to go to the right with some probability. And then at this vertex, it either goes up or to the right. And in this case, say go to the right. You have 2 particles coming into a vertex, sorry, 2 arrows coming into a vertex, they both have to go out. So this corresponds to this particle jumping 2 steps to the right, and this particle jumping 1 step to the right, and I guess it leaves the lattice. Okay, so what's the algebraic structure underlying this? So there are these things called affine Lie algebras. So as a vector space, you tensor with Laurent polynomials in T, and then you need to take a central extension. So affine Lie algebras are pretty interesting. So one thing it does for you is that because you have an additional term T, you now have a family of 2-dimensional representations, letting T act as multiplication by Z. So now you have 2 parameters Z and Q, and these correspond to the 2 parameters B1 and B2. It's stochastic 6 vertex model. So of course, affine Lie algebras are much more interesting than just giving you another parameter. But at least one thing you can get out of it is you can look at 2 parameter models now. So if you try to use duality using the same approach as before, the Casimir element is now infinite. It's not infinite because this vector space is infinite dimensional. So for stochastic vertex models, you're going to need a different approach. And it turns out the thing we'll need is something called the R matrix. So the coproduct is not symmetric, right? So it's not equal to its reversal, but it's almost symmetric in the sense that there's an element called the R matrix that intertwines between the coproduct and its reversal. So if you know Hopf algebra terminology, I think it's almost co-commutative. And this R matrix is actually in a representation, gives the vertex weights of the vertex model. And the R matrix is more famous for satisfying the Yang-Baxter equation. But as far as duality is concerned, we don't explicitly need it here. So in this paper by these 4 authors, they have some explicit formulas for R matrix of a higher rank Lie algebra. So SLN+1. So this is the n species model. S1 plus 1 hat, I should say. And fortunately, they gave an intertwining between R and its transpose. So the model is no longer reversible, but you have this nice property that sort of plays the role of reversibility. So with that at hand, you could define stochastic vertex model on closed boundary conditions. So the thing I said before to open boundary conditions. So you can just seal off the right boundary by just having all the particles stick there. So that's a step that needs to be done. And then the stochastic vertex model is dual to its space reversal, and it's actually the same duality function as the multi-species ASEP QJ. So that's not clear to see probabilistically, but algebraically, it's a little more straightforward, and that's just because you're embedding G into G hat canonically here, so just G tensor 1. So the duality function is just the same. It's just the same element in the affine Lie algebra. And then, so when there's only one species of particles, n equals 1, you recover previously studied models. So that's not really that immediate either. So you have to do some calculations to verify this. And you can also view this model as n coupled copies of single species models. And then if you take degenerations to Q boson and ASEP, then you get these, you get the dualities I mentioned before as corollaries. Yeah, and the proof of duality, as I said, it's an duality is intertwining, and it uses this intertwining of the R matrix. Okay, so sorry, the font's a little weird. So these are just some of the things I talked about. Okay, so that was the first step, which yeah, duality reduces the infinite particle system to a finite particle system. So once you have the finite particle system, you need to analyze it somehow. So I'm going to give the result for, I'm going to show you the result for ASEP to see what these formulas look like. So for ASEP, if you have particles starting at y, you want to know the probability to end up at x. You have a sum of contour integrals, the sum over permutations of n letters. And each A sigma is a product over inversions. You have some function S, sometimes called the scattering matrix. And then, sorry, this should be alpha and beta instead of P and Q. So in the totally asymmetric case, the sum over permutations just becomes determinant. But in general, it's just a sum of permutations. And then for Q boson, you have a similar formula. Sum over permutations of a product over inversions. And scattering matrix is this form. And then you have some prefactor, depends on factorials of occupation variables. So there's a algebraic action on particle configurations. So if you just consider particle configurations, you have two natural symmetries. So you can permute the particles at a single site or permute particles of the same species. So if you rearrange like these third class, and fifth class particles, that preserves it. So there's 3 here, 2 here, 2 here, 1 here. So you have this Young subgroup S3 cross S2 cross S2 cross S1. Or if you switch these 2 second class particles, that preserves it. Same these fourth class particles. So it's 1, 2, 2, 2, 1. There's 1 first class particle, 2 second class particles, and so forth. So you view H prime, yeah, so if you one of the actions is the left action, the other is the right action. So each particle configuration can be viewed as an element of a double coset. So it's a factor combinatorics of Coxeter groups that you can pick a coset representative with the fewest inversions. So this allows you to represent each particle configuration uniquely as X sigma. So X tells you the particle locations, and sigma tells you how the species are ordered. So here, this starts at the 2 because the first class particle is second farthest to the right, and then the second class particles first and fourth farthest to the right. And so with this interpretation, so the general formulas, so starting with generic initial conditions, I don't think the formula is going to simplify. But you can consider Q exchangeable initial conditions, where the initial conditions are weighted proportionally to Q to the number of inversions of sigma. And it has this pseudo it's a factorized form. So the second line here only depends on X, and this first line only depends on sigma. And the prefactor Wx actually just turns into some statistic depending on the combinatorics of the symmetric group. So you basically just show that Q exchangeability is preserved, and you do some combinatorics of the symmetric group to match the prefactor there. Right. So then, and then here's a similar form as the ASEP. So the fermionic case where there's only one particle, it's a little simpler. One particle is a little simpler. Okay, so the last few minutes, I'll say a little bit about the last step. So in Tracy Whittam's work, the most interesting part isn't actually the Green's function. It's this miraculous symmetrization identity. So you had this sum over permutations. But if you look at the probability distribution of the rightmost particle, it's just a single integral. And that's because the sum over the permutations, in their words, it's miraculous, simplifies to this term here. So it turns out, if you consider a multi-species ASEP, then this Tracy Whittam result here follows from the Green's function from a few slides ago, pretty quickly, about half a page. So we actually don't need to prove a symmetrization identity. So originally I was looking for a multi-species version of this symmetrization. But somehow when you go to multi-species models, calculations become easier, which was a little unexpected for me. Okay, and then for the Q boson, if you take, for Q boson, you can have infinitely many particles at a site. So you take all particles starting a single site. So you have this symmetrization identity that Wang and Hua proved. It's maybe a little bit less miraculous, but it still needs to be done. And they consider a inhomogeneous model. So you can have different, you can have scaled jumpers at each site. And now you just have this single contour integral. Okay, so yeah, this is going to get a little technical. I guess we're getting to the end now. So it considers suffice to consider where you have one particle of each species, and you can take all particles starting out in a single site. You can set to be 0. And you have this sum of large contours. So all these contour integrals are the same. And you have just some constant in front. And the way you get this, right, so you're fixing locations of k particles, and then you sum over k+1 to n particles being bounded on the right. So you take the sum, it's a geometric series, but it turns out you get a lot of cancellations, and it's a telescoping sum. So each time a jth class particle moves over a j minus first class particle, that adds 1 to the number of inversions. So you have to have a q here. And it basically turns out that B has this nice property that B times this thing is this term that's anti-symmetric in 2 variables. So because all contour integrals, all the contours are the same, if you take the integral over an anti-symmetric term, you get 0. So you get a lot of cancellations, and you only have a pole at 0. And then b evaluated with the last variable at 0 is just another b. So each time you do a sum, it reduces an n-fold contour integral to n-1-fold contour integral. And then the next time you do reduces this to n-2-fold contour integral. So eventually you get a sum of k-fold integrals up to n-fold integrals. And then it turns out that you can make a deformation of large contour integrals to small contours. So these are no longer the same. So these are nested contour integrals around 1, but not around 0. And when you make these deformations, you pick up residues. And it turns out that everything cancels except the n-fold contour integral. So before I had this constant, so you see this constant, maybe you just think that's kind of messy, and it is kind of messy. But that constant turns out to be exactly the constant that you need to make everything cancel except the n-fold contour. Yeah, then you take k equals 0, and then you can check directly with previous result that these are the Q moments of the yeah, these are the Q moments of the Q boson. Yeah, so there's just yeah, they just do this by taking the equation and showing that it solves the differential equations that it needs to solve. Okay, so then I'm wrapping up here. So just next steps that I'll do. So I said, you have single point fluctuations in multi-species models to try to prove something that's more general. And then analogous results for ASEP. Okay, so yeah, I think guess it's about 10 o'clock, so I guess I'll stop here. So yeah, I have no more math slides anyway. So yeah, thank you for listening.
Okay, thank you, Professor Kuan. It's a wonderful presentation. Very interesting. Aaron, do you have a question?
Oh, I was just unmuting to clap, but I do have a question. If anyone else has a question, they can also jump in.
Yeah, I think that's a great time to ask your questions.
Yeah. All right. Apologies if you mentioned this before and I missed it. Why is the ARE2 process, is that named that because there's some relation to the ARE function?
Oh yes, that's a good question. Yeah, so the Tracy-Widom distribution can be written as the Fredholm determinant of a kernel, and the kernel is written as the integral of ARE functions.
Oh, weird.
Yeah, so that's why it's named the ARE process.
Cool.
Yeah, and then yeah, there are different statistics you can look at in different scalings where you can get like something called the Parisi process, where it's the Fredholm determinant of a kernel that depends on the Parisi function. So yeah, that's why it's named ARE.
I guess another quick one, also which maybe you answered already. So if you look at that like height function for the original process, like for the symmetric exclusion process, or maybe for the asymmetric exclusion process, is there like a limiting form for that curve?
Oh yeah, let me go back. So you mean like this curve here, right?
Yeah.
Yeah, it's explicit. It's pretty simple. It's just a parabola.
Oh, right. You said, okay. That's a little weird. Okay, right. It's a little weird to me because, at any time, it's going to have, slope 1 asymptotes to the left and right. So it's kind of hard for me, to me, like a defining feature of a parabola is that it doesn't have asymptotes like that. So it's a little.
Oh yeah, sorry. I meant to say it's a parabola in this region and then straight lines. Yeah, so it's the straight lines outside and then in the middle it's a portion of a parabola. I guess this is more accurate.
I guess what I mean is Well, okay. Is the parabola scaled somehow? So at the, at the gluing points, it has slope 1.
Yeah,
Okay.
it's scaled a certain way. Yeah.
That's interesting. So I should think that it's the. Okay. If you don't know a lot about parabolas, a parabola doesn't have any sort of scale invariance, right? So should I be thinking it's like a larger and larger portion of a parabola, which is then like sort of squashed?
Yeah, I think that's a good way of thinking about it. Yeah.
Okay. Thank you.
I want to ask about, is there like interdisciplinary approach for problems on this topic, such as some question potentially can be solved by computation means, because you mentioned several computations also.
You're asking if there are just computational experiments you can do, or you mean like similar to like this thing?
Yeah.
So you can try to do like multi-point fluctuations for this model.
I see.
Another interesting thing I think is and then there's this other thing I mentioned here about the crossing probability. Because there's, in principle, there's more than one question you can ask on multi-species models, just because there's more going on. So maybe trying to figure out what like crossing probabilities for ASEP, for 2-species ASEP, for example. Yeah,
I see.
Yeah, computations are helpful.
Yeah, sounds very interesting to me also.
That's part of the reason I tried learning a little bit of Python.
Okay, do we have any other questions from the audience?
So speaking of computations, when you were doing the supercomputer experiments, is there some, I guess, clever method that one can use to sample these processes? Or are you sort of very literally like, generating these exponential clocks and then checking to see which jumps are allowed and so on?
Oh, yeah. So I'm not very good at computer programming. So there's probably a clever way of sampling it. What I did was actually just what you said. I just actually ran a bunch of exponential clocks. Yeah, so that's why I needed the supercomputer, because by the time 2000, you have way too many particles for my laptop to run effectively. So
yeah, I was surprised by that, because it didn't seem like enormously large numbers of things. Do you have an intuition for why the problem is so hard?
I think it's just, when it's first starting, you only have maybe like 1 or 2 or 3 particles to keep track of. But once you have 2000 particles, at time 2000, you may have like 2 or 3000 particles to look at. So then, so because the clocks are independent, each update occurs every, like, on average, 1 out of every 2000, 1 over 2000 times. So each time you go up, you have to update 2000 times. So then
I see.
So it starts running a little bit slower.
So to run this model for that amount of time, you have to run something like 1.5 million updates.
Yeah.
I see. Okay. And you're saying you have more particles to track as time goes on, because you can, when particles are in the C sort of that extends out to the right, you can just pretend they're not there.
Yeah, exactly. Yeah, I also didn't write a very efficient program. And also like the TextAM supercomputer gives us like 5,000 computing hours for free. Nice. So I didn't feel the need to conserve my credits.
Yeah, that's really interesting.